Good morning. Hope everyone is doing fine. We have got a midterm coming up and a final not very long after that. So here's a set of review problems that we put together. It's just one set from a collection from some different previous year midterms. And just kind of talk about some of these problems and then maybe expand on these a bit. Thinking about what kind of problems could show up. So here is, here's a solution on problem one. Problem one says that we have a long solenoid. So we've been using solenoids for everything, right? You're thinking of renaming the course, the solenoid course. This solenoid has a radius of r, and it's long enough that we can consider it to be a solenoid. Okay, so all the solenoid approximations that we've been working from. It says that this has n number of turns, has a length of L, and it carries a time-varying current. So that's kind of interesting. If I have a current that's varying, this is varying like the cosine function, then the magnetic field inside will also be varying. If we have a varying magnetic field inside, then if we have a varying magnetic field in this region, then these wires that are surrounding, or the one wire that's surrounding the solenoid, we're going to induce a current. So we know that when we have accelerating charges, the varying magnetic field is telling us that we have charges that are accelerating. Charges are not moving at constant velocity. Constant velocity charges would create constant magnetic fields. But the magnetic field's varying, so we do have accelerating charges. And accelerating charges will generate electric fields, kind of different shaped electric fields than we saw in the early chapters. Just in these recent chapters, 29, 30, 31, we've started to look at accelerating charges and what the electric and magnetic fields will look like. Now, all of this can be summarized in what's called Faraday's law. So we can certainly work from Faraday's law to calculate that, and in fact that's what we want to do. It says that if I follow the electric field that's been set up in this region of space where I'm going to place the wire, I want to find out how much electric field we have. There's going to be an EMF, I should have put EMF right here. The EMF that's generated will be a result of those electric forces. We've got these looping electric fields, We've got these looping electric fields, and they're going to push charges through the wire. So we've seen examples of where magnetic forces are pushing charges, and we've seen examples of where electric forces are pushing charges, and either one will work. I always feel like it's unfortunate that textbooks often present, I believe, is my bias, Faraday's law as if it's a new force of nature, and it's not. Faraday's law is just a very useful formula that allows us to relate the effects of accelerating charges. It says whenever we accelerate charges, we're going to be varying magnetic fields and electric fields in a way where the pattern is that those electric fields, if I integrate along the looping electric fields, those will match up with the time derivative of the magnetic flux. So again, it's one of those high-level theorems. It's remarkable to me that people are able to mathematically derive these things, but that's what we find. So we can use Faraday's law to be able to go in and see the effects of these accelerating charges. So the flux in this case would be the magnetic field times the cross-sectional area. Here is the magnetic field inside the solenoid. Now the area where the magnetic field actually exists only has a cross-sectional area of pi r squared. So if I'm looking at that loop, see that loop where we're trying to match up the electric field along that path of integration. So our integration path is along where the E field is that we're trying to measure, because that's the EMF that we want to calculate. but the magnetic field is really only in this region. In reality, when we get outside of the solenoid, there are magnetic fields, but they drop off very rapidly. So we're kind of ignoring the magnetic field outside of the solenoid and sticking with this approximation. So that tells us the flux. Now, Faraday's law tells us, well, let's integrate the left side. So, you know, we started out, we had Gauss's law early in the course, and we've gone through a series of these, Ampere's law and now Faraday's law. Two Gauss's law, I guess, and Faraday's law makes 4. So on that left side, that's a path integration. It's E times the circumference. Now the circumference is 2 pi little r. And then we have to take the time derivative of the right side, the flux formula. Now, when I look over here and I'm looking for time dependence, everything's a constant except for I. I is the only time dependence. So that's what we've shown here, is that I is a cosine omega t function. Di dt is going to be minus omega I naught sine omega t. And so putting that all together, we now have, instead of I, we have the constant I naught, and explicitly written out as an extra factor of omega, and then sine omega t. So that tells us how much EMF we're going to generate in that outer loop. It's kind of like making a transformer, right? We've got one side, here's the primary side of the transformer, and this is going to be just one loop, but it's the secondary side of the transformer. And by accelerating charges, oscillating the charges, accelerating them in the primary, electric forces, in this case it's electric forces, are going to oscillate the charges on the other side. Okay. In a transformer, the effect is propagated through the spins of the electron in the iron core. Anyway, in this problem, it's more direct. The loops are wrapped around the other loops. So we're going to come back to this equation, bring the 2 pi little r over, and that's it. That's what we've got for the electric field. Now, we wanted to get the EMF. Oh, and it even says I wrote transformer. So it is. It's kind of like a transformer here. So the EMF will be the E field times 2. What did they ask for? They derived an expression for the electric field. So we got the electric field expression. And it says that the strength of the E field, and therefore the strength of the EMF, will depend on how far we are away. If we want to get the best effect, we want to get that loop pretty close in, so it's just wrapped right around the solenoid. Let's get that inside there. We'll get the full flux in that case. And then there's a factor of omega. So if I oscillate this faster at a higher frequency, well, that's a higher acceleration, right? Higher frequency of oscillation would be a higher acceleration. That's going to give us larger electric fields outside that region. And then, yeah, the transformer thing here is just, those lower diagrams are just showing how I and dIdt are related. So we're looking at the dIdt, which is what the electric field depends on, is 90 degrees out of phase with the current. When the current peaks, the EMF in the outer region, or the electric field, is 0. When the current is changing rapidly, and that's when the current's 0, is actually when it's changing most rapidly, that's when the electric field and the EMF are the very largest. All right, let's go ahead and move on to the next example here. So here we've had so many circuits in these let's go ahead and call them 4 chapters. So chapters 29, chapter 30, chapter 30, and chapter 31, those are the 4 chapters. I know I counted chapter 30 twice, but that's because it's one chapter inside there is on inductance and the other chapter is on AC circuits. Come on, it's 2 chapters, right? So, and here is one of those circuits. Now, this is not the AC circuit. This is the early part of the chapter, the first half, chapter 30A, where we're looking at inductors. And so we've introduced the idea of inductors. We're still using direct current batteries we're using for our voltage. What's going to happen when we close this switch, and everything's described in that problem. Oh my gosh, this goes through F, part A, part B, part C, D, E, F. That's a lot of parts. That first problem just had one question. And okay, so on A it says, at the 100 millisecond mark, calculate everything. Okay, so we're going to close the switch at t equals 0, and then we're going to wait 100 milliseconds and take a snapshot of everything that's happening. And apparently we're going to measure the current, the voltages, the potentials, the power of the battery, power being dissipated in the resistor, and the power of energy storage. They're all powers. The rate of energy storage in the inductor, that's a power too. So current, voltage, power, power. Those are the 6 things we've got to calculate here. So let's see, we're just going to follow that formula. I naught is going to be given by V over R. That gives me 1.20 amps. The time constant for an RL circuit, or an LR circuit, is L over R. That gives us a time constant of 200 milliseconds. Here's all the givens. Here is the 200 milliseconds. So we're only halfway through one of the time constants. At 100 milliseconds, that's only half of the time constant that we have included. The current worked out to be 472. Now the current's going to be rising like this. Eventually the current is going to hit 1.2 amps. We only went through half a time constant, so we got a long ways to go. We're only at 472 milliamps, but that's what the current looks like. Let's see, we said current, voltage. Here is the voltage on the resistor at that time. So right at that instant, the voltage on the resistor will be R times whatever the current is right at that instant. So I got to use the current at the 100 millisecond mark, plug that in. It looks like right at that instant, the voltage across the resistor is going to be 4.72 volts. Now, for the inductor, we would think, since this is a DC power supply, the battery, that the voltage in the resistor and the voltage in the inductor have to add up to the combined 12 volts. Let's see if they do. To calculate voltage in the inductor, we need L times di dt. I went back and solved it. So di dt is equal to I naught over tau e to the minus t over the time constant. And that, using the values for I naught and for tau, that reduces or simplifies to V over L. So it's V over L e to the minus t over tau. I plugged that all in, and I got 7.28 volts. So this is a way to check the problem, right? See if I've got, if my answers are consistent, and my 2 voltages calculated independently by my V sub R and V sub L formulas, they do add up to be 12. 12 volts total. Looks good. Let's see. Oh, now we got the power. So we got the current, voltage, power. Remember, VI, right, for any individual device, whether it's a battery, a resistor, a capacitor, an inductor, any of those, I can calculate the power. Now, power is an energy rate. So I got to think in terms of energy rates, I guess, the rate at which energy is doing something. And so for the battery, I can take V times I. Now the I, right at that instant, was this 472 milliamps. That says that the battery is supplying 5.66 watts. Right at that instant, the battery is in the process of putting 5.66 joules every second out into the circuit to let the resistor and inductor do with what they want. So the power in the resistor, I can take the voltage times the current for that, that's 2.23 watts. So of the energy that the battery is supplying, this is the rate at which energy is coming out, this is the rate at which the resistor is using that and converting it into thermal energy. all right? And that's gone, that's not recoverable, that's just gonna spread out into the environment, right? So, I mean, if you've got a, you know, if you're heating up something, that's useful. But that energy is not in the circuit anymore. Now for the inductor, it's amazing, but I can still use V times I. I just have to make sure I'm using the V for the inductor and the I for the inductor. Now the current is easy in this case because it's a one-loop circuit. For one-loop circuits, everybody's got the same current. So once we have determined the current for any device, well, I guess we generally solve for the current. This applies to everybody. So I just keep plugging that current in and multiplying by the different voltages. So this worked out to be 3.44 watts. Now what does that mean the inductor is doing with that energy? And it's storing it away. The inductor is building up a magnetic field, it's storing energy in the inductor, and that's the rate at which it's stored. So the powers match up correctly, the voltages match up correctly. It looks good, right? It looks like there's a good chance that we've done the problem right, maybe. Everything seems to match up. We can put a little comment at the bottom of the page. Everything looks like it matches up. Of course, it looked like things matched up last time too. Let's see, here's problem 3. So problem 3 says, now we got to read this careful. So I want to say this was clearly chapter 29. And this was clearly the first half of chapter 30. Now this is an AC power supply. This is the, not the first part, the last part of chapter 30. So this is coming from, this is from 29, 30, 30. Ooh, that looks like 31. So I think we have, you know, one problem from each one. On this one we have a resistor, a capacitor, and an inductor, and they're all in series. That's important. And it's in series with a 60 hertz AC source with 110 volts. That sounds kind of like an outlet, right? I mean, we've been talking about the outlets as officially being 120 volts, but often you see this 110 volt thing get listed too. So anyway, it sounds like it's just an outlet. And we have plugged in series, here's our picture. Here is the AC power source. Now remember, there's two values we need, two properties that this has. One is the voltage and one is the frequency. Now, the voltage could be given as peak voltage or it could be given as RMS. And they're telling us that it's being given as RMS. So that means through the rest of the problem, either I do everything with RMS voltages, RMS currents, average powers, or at some point I do a conversion and do everything in peak. Either way works. We can switch back and forth as they tell us to. So unless something else happens, it's just everything, and it looks like everything got completed in RMS. So let's see, here is the resistance, here's the capacitance. Now they tell us we don't know the inductance value. We're actually hoping to be able to find that by setting this up. So it looks a little bit like our inductance lab. Okay, we didn't have capacitors, I think. We just had resistors. But it looks a little bit like our inductance lab that we did, where we went in and measured the inductance of some samples. So let's do this. Let's write down the frequency. So I'm switching over into omega, 377 radians per second. And then the other item that they're supposed to tell us here, yeah, it says the RMS current is at 150 milliamps. So that is the RMS current that we're looking at. Okay. All right. And so to calculate the total impedance, Z, we can take VRMS over IRMS. That works. And we're going to get 733 ohms. Now, I started writing some impedance diagrams, because the impedance diagrams are so, I think, they're really very, very helpful. They allow you to maybe see things that you wouldn't see otherwise. So in this case, what we've got is Z, we've determined to be 733. Now, the resistance, we've already been told, is 480, and the capacitive reactance, 1 over omega C, is going to be 1001 ohms. So those are the possibilities that we have here. Now, there's a couple ways this diagram, might work out, and that is, yeah, I don't know if I quite got these to scale. I guess I should have paid closer attention to make sure I was getting these to scale. So what we've got here is a couple possibilities. We could have that, we have a positive phase angle, and that would say that the current is out ahead of the voltage, or the voltage is out ahead of the current by some angle, and we could assign Z to that direction and R here. So what we've got is, we've got those two numbers, and so 733 here and R here. That's going to tell us what XL minus XC needs to be equal to. Here is the Z squared minus R squared square root, and it says that this combination of XC and XL needs to be 554 ohms. So that's, that's a fixed amount that we have to come up with. Now, there's two possibilities. It could be that XL is bigger than XC, or it could be that XL is smaller than XC. Those are two distinct possibilities. So it could be that the reactance in the inductor is equal to XC plus 554. And if I do that and take this 1001, that would say that the inductive reactance is at 1,555 ohms. And calculating for the inductance, dividing through by the omega, gives me 4.12 Henry. So that's a lot of Henrys. In lab, I think we had those big inductors in lab. They were about a Henry, I think. Some students, I don't know, I guess in the past, some students, we've got now several inductors. I think we might have done this in the video. Got out several inductors and kind of lined them together to see how large we could get the inductance. Anyway, that's a fairly large inductance, but it's not crazy. So 4.12 Henrys. Now, the other possibility is that XL is less, and that would say that in this case, the L would be a smaller value, 1.19. So let's see how we did this. I'm a little concerned that we didn't get the XCs to scale. So the R's were 480, the Z's were 733. That looks okay to me, that measurement. But the XCs are going to be big, so I should have drawn the XC all the way down to here. And then I should have drawn the XL even bigger to offset that. Would have been the correct drawing. So I apologize for that. I should go back and get those so they're more useful. And then in this one, the XC again is fixed. It's at the 1001. So that's going to be the same part of the drawing. And then in this case, the XL won't be quite as large, and it'll be the XC that dominates in that example. Okay, so that's kind of the problem. What value of inductance would produce a resonance circuit? So in the later part of the problem, where is that? Oh, I guess it's here. Is that part B? Am I standing in? Yes, I am. Part B, we want to say XL and XC. We want those to be the same. We want them to be 1001 hertz, and that's something in the middle. So if we have an inductor at 2.66 Henrys, that'll do it. So at 4.12 Henrys, the inductor is dominating 1.19 Henrys. The capacitive reactance is at 2.66 Henrys. Everything is in resonance, and the resistive effects from the capacitor and the inductor will cancel out, and Z then will line right up with R. Z will be equal to R in that case. Okay, so this is a good, that's a lot of good stuff in that for an AC circuit problem. All right, here is our last question on this practice set of 4 problems. Again, make sure you're looking at homework, make sure you're looking at examples from lecture as well. These are just 4 problems. They have shown up on previous year's exams, but they're not, you know, something similar could certainly show up on our midterm, but something similar to the homework or lecture problems could also show up. All right, let's see. It says that we have a microwave source. We have these 1 nanosecond durations of microwaves, that's very short, in a beam of a diameter of 12 centimeters. So I got a beam about this big of microwaves coming through. The average power during each pulse is 25 kilowatts during that time. What's the wavelength? What's the total energy of each pulse? Calculate the average energy density in each pulse. Determine the amplitude of the electric and magnetic. Okay, so it's kind of all that energy storage stuff in propagating electromagnetic fields. Okay, I mean, we call them electromagnetic waves, but as we've been talking about in class, these waves don't have to be wavy. So it's not, anyway, they're propagating electromagnetic fields that we're looking at. Now, in this case, let's see, that 1 nanosecond's got me kind of worried. That may be too short. Let's take a look and see what we've got going on here. The frequency is 20 gigahertz, so I got the gigas in there, and from that I was able to calculate the wavelength by taking C over frequency, and what I'm seeing is that this is about 15 millimeters, yeah, as a wavelength. So the wavelength is pretty short. Electromagnetic fields propagate at the speed of light, and in 1 nanosecond they only travel about 30 centimeters. So the entire pulse is only about, well, there it is right there. There's the pulse right there. It's a little cylinder pulse. So this is 30 centimeters, and these wavelengths are 15 millimeters. That means you can only fit about 20 wavelengths into that. But that's, you know, maybe that's doable. So about 20 wavelengths fit inside that, that distance. The energy that we have in each pulse, we can take by the power and multiply that by the duration, and that gives us 25 microjoules. So that's B. Is this going to be another one that goes through the alphabet? A, B, C, D, E. We've got the energy of the pulse, we've got the wavelength. Now we got to get the energy density. Okay, so we took kind of a different route from the textbook. I hope it's been easier. I hope you found that solving a lot of these homework problems has actually been easier the way we set up these different quantities. In any case, that's a big U, that's energy. This is a little u, that's energy density. And the intensity is U times C, which is power divided by area. So if I solve for the energy density, I can get that by looking at the power, dividing through the cross-sectional area. There it is. I did solve for area. So I've got area up there. It's 0.0113 square meters divided by C. 7.37, 10 to the minus 3 joules per cubic meter. So for every cubic meter, I guess the beam's not that big, is it? But the energy density is such that if there were a cubic meter, I guess I should have scaled it down. 7.37, 10 to the minus 3 joules of energy contained. Now the energy density assigned to the electric field components versus the magnetic field components, those are the same. They're evenly divided. And so I can take half of that number and assign it to the electric field energy density and the magnetic field energy density. And then I can work back through these formulas to calculate E and E fields and the magnetic fields. Now remember, once we've added a factor of C onto the magnetic fields, the formulas all just match. And so at least in this first step, I am going to solve for C times B. So both the electric field and the magnetic field using unified units are going to come out to be 28,900 newtons per coulomb. Okay, so that's how large the electric fields are inside these pulses, and there's that cylinder of pulse up there. Now I did convert this back over to Tesla. I divided through by C, and that turns us into units of Tesla, and it worked out to be 96.3. So as we've mentioned in lecture, this in some ways is a better way to think about these electromagnetic fields that are propagating. The electric and the magnetic fields contribute the same amount of energy. They should both have the same magnitude, and using this formalism allows us to show that. Now, when you look at this number in Tesla, you go, wow, that's such a tiny magnetic field, but that's such a large electric field. But they both have the same amount of energy stored, okay? Same energy density. So again, another, advocating a bit for thinking, at least conceptually, in those terms. And then finally, we can get the force, we can get by taking the power and dividing by C. So if this were to be completely 100% absorbed on a surface, power is calculating the energy coming in, dividing by C, converts it from energy into momentum, and that's what force does. So 83 micronewtons, we're not going to be collapsing any walls, shooting this microwave beam at them. Although you could push, small objects that don't have much size to them, this beam could really push them around. So there were some examples we looked at in lecture with that. If you have tiny, tiny objects, a beam like this could exert effectively a large effect, a large acceleration effect on that object. If this were a perfectly reflecting surface, this number would double, because it would not only be absorbed, but it would be re-emitted, is the way to think about it. That represents twice as much momentum shift. So bouncing off would create twice as much force. All right, that's it. That's the practice set of problems. I hope those are useful. I think they are. I think we've been able to discuss quite a few topics, starting from these and kind of thinking conceptually how to go through this. We've got one example from each chapter, so everything seems pretty good. So if you guys have questions, definitely stop by office hours. Let's get those looked at. Let's talk about whatever questions you guys have. The fourth midterm is coming up, and the final exam is soon to follow the week later. Have a good day.